learn how to speak Chinese.
Hey, I'm Viscosity Lab, and I'm also a mechanical engineer.
And I'm Fatima Abdullatif, and I came from a country where women can vote but cannot drive.
And I'm Darren Huggins, and I've won 11 intramural championships.
The objectives of the Viscosity Lab are to experimentally determine the viscosity of your given fluid using two different apparatuses. One, the Brookfield viscometer, which is over my left shoulder on the countertop, and the other, the falling sphere viscometer, which is over here. And compare them to the literature values that you find for your fluid.
Hi, I'm Viscosity Lab, and I'm going to be showing you how to use the falling sphere viscometer, which is right here. These are the spheres you'll be using. There are four different types of materials. You have brass, glass, aluminum, and plastic. Each sphere has a different size diameter, so you'll see you have large brass spheres here, large aluminum spheres here, and you will need to measure those diameters using this caliper. So to use an aluminum sphere as an example, use this knob to open up the caliper. Place the sphere, try to center it using one hand, and then tighten the caliper with the other hand. Tighten it, but don't over tighten it. You just want to squeeze it enough to hold it in place. And then read the value in inches on the scale there. Once you've measured the diameter of the sphere, you'll need to measure the mass of it using the analytical balance. After you've done that, you can come over here to the falling sphere viscometer, turn on the light by twisting the switch here. Notice you have three kinds of oil. For this year at least, it's silicone oil, glycerol, and mineral oil. Each group will be assigned one, so you'll need to know which one that is. Climb up the step ladder. You'll need to wet the sphere with your assigned oil and try to get out all the air bubbles that are around it. Once you've done that, drop the sphere. Try to drop it in the center, not on the edges, or else that'll mess up your results. You want to just let go of the sphere, don't push it, don't twist it. As the sphere falls, one of our teammates is going to time how long it takes for the sphere to fall from the starting line to the stopping line. So, I'll show you guys how to do that. Ready? That is one trial run. You'll need to calculate the Reynolds number each time you do this. You want to make sure your Reynolds number is at least less than 2, preferably less than 1. Otherwise, your calculations aren't going to hold, and you'll have to come back in and do this all over again, and nobody wants to do that. You will need to wear gloves. This stuff is messy. And lab coat, because this stuff is all over the place. And it's gross. So that's how you use a falling sphere viscometer, and now Darren will show you how you use a Brookfield viscometer.
Hello, class of 2013. This is my friend the Brookfield viscometer. As you can tell, it has a lot of buttons, so I'm about to walk through with you what everything entails. The first thing you want to do when you're going to work with this is you're going to look on the back. There is a level that lives back there, just like you would have for carpentry, that has a bubble, and you're going to want to put it right in the middle of that circle. Next, what you're going to do is we're going to stay back here. We're going to look at this knob on the side right here. Whenever we're first turned on, we want it to be at 12 because I'll tell you why in a second. So first you have to zero it so it knows what it's doing, because if you don't zero it, it's going to be confused. So the first thing we're going to do is we're going to power on, make sure the RPM thing is turned to 12. We're going to turn the motor on, just a switch on the right, then we're going to auto zero it. It's going to crap out for a couple seconds, but after it stops crapping out, it's going to give us a reading. which will be 0 because it's auto zeroing. Boom, perfect. Next, we want to turn off the motor, and it's going to be in standby mode now. So it's going to go back out to 0. It's in standby mode. Next thing you want to do is you want to choose a spindle. Choose your spindles wisely. There's 4 to choose from. You're going to use 3. I'll use this big one just because it's easiest to tell what's going on for this demonstration. What you're going to want to do is you're going to want to lower this down so you can put this at an angle into the water, and then you can be able to like screw it on while it's still in the water. So we're going to lower this down. There's this knob all the way on the right that we can lower it down with. Alright, and you're going to want to put the spindle in at an angle to avoid getting air bubbles in it. Next, you're going to screw it in. You're going to have one hand on the spindle, one hand on the screw, and it's counter to every other screw you've ever used. It's a left-hand screw instead of a right-hand screw. You want to put it on tight, but not too tight. There's actually a pinch point right here, so be careful with that. Don't pinch yourself. Finally, we're going to want to lower it down the rest of the way into the liquid. I don't know if you can tell, there's a little notch right here, and that's the water level notch, and you want it to be right there, or the liquid level notch. All right, once we're in here, you're going to want to enter the spindle number. The spindle number is right towards the top. This is spindle 1. You go over to the book. It's on page 16. This book will be given. And spindle number 1, the spindle entry is going to be 61. So you come back over to the viscometer. You hit the spindle button. And you hit 61. And that's 11. So we're going to hit the spindle again. We're going to put 61. And it's ready to go. We hit the CPS. That's centipoises. So it's going to measure in centipoises. And then we go ahead and just flip it on. Water has a really low viscosity, so it's still trying to zero out because the viscosity is so low. This is kind of cool water, so it's going to give us a little bit higher. Water's viscosity is about 1, it's giving us about 3, 2.5. That's just because the water's cold, and this machine probably hasn't been calibrated in a while, and there's a lot of air associated with your typical user. And that is how you use the Brookfield viscometer.
Thanks Mustafa and Darren for explaining the equipment that we'll be using during this lab. There's some important safety features that you need to make sure to do anytime that you're in lab. Especially for this experiment, you're going to want to wear gloves. So we're going to put some on. The fluids are pretty viscous and sometimes they don't wash off very easily. So you don't want it to come in contact with your skin. Along with wearing gloves, you also want to make sure to wear long pants and closed-toed shoes. For this lab, if you're going to be using the falling ball viscometer, you're going to want to be wearing an apron, just in case it gets on your clothing. So the fluid won't wash out of your clothes, it might leave a stain, and nobody likes clothes with stains. Also, whenever you're using the falling ball viscometer, you're going to make sure to carefully climb up the step ladder. It's a few steps high, so you don't want to fall off. And when you step onto it, it's going to pressure release the stopper, so they won't be able to move. When you're up here, just be careful whenever you're putting your stuff in the fluid. You don't want to accidentally spill it out, and people can trip because it's really slick. Whenever you're going down the ladder, be just as careful. One thing that Darren and Mustafa left out of the procedure was make sure to measure the temperature of the fluid, so you can correlate that to your densities and the viscosities. In the event of a spill, make sure to come over here and get the mop and bucket. Use the mop to clean up whatever you've spilled on the floor. And also, put out a caution sign, just in case it's still slick. Especially with the fluids that we're using in this lab, they won't clean up as easily, so you don't want people to slip and fall. Also, don't forget to wear your safety goggles. You definitely don't want to get it in your eyes.
Hello, I'm Fatima and I'm here to discuss theory through calculations. This lab is an application of the Stokes law. A falling solid sphere and a viscous fluid usually experience different types of forces: the gravity force, the buoyancy force, and viscous forces. If you would apply the force balance to this wall, you will get the of gravity force would equal the sum of buoyancy plus the viscous force. Sorry. The Stokes law is only valid if you ignored or neglect the inertial forces, and Reynolds number for your sphere must be small. For this calculations in particular, Reynolds number must be smaller than 1. If you arrange this equation, the forces balance, you would get an equation to calculate the viscosity. D is the diameter of the sphere. This is the density of the sphere, density of the liquid, and Vt is the terminal velocity for the falling sphere. Once you calculate the viscosity, you will need to calculate the Reynolds number for each try. For each sphere you have tried. Reynolds number must be less than 1. If you had a larger number for Reynolds number, you must redo your calculations, or you may have to start again your experiment again. For Stokes' law, when you want to apply this equation, there must be some assumptions that are valid. First, as we said before, neglect inertial forces, and that's only correct if we have small value of Reynolds number. Second assumption is the falling sphere must reach a terminal velocity, must be at a steady state. 3 is unbounded fluid. That means you don't have, when you release your sphere, you don't disturb your fluid. And that's only possible if you try to release your sphere at the center of the column. 4 and last is Newtonian fluid. You won't be able to know if your working fluid is a Newtonian or not, but when you've done all your calculations, if you got a rough same velocity for each of your trials, then you can tell that your fluid is a Newtonian.
Thanks for watching the video. I hope it helped you